Welcome to the first content lecture of ECH 4123, where we'll talk about some review that you may need from previous courses. Just as a quick stylistic note, this will typically not be the format that I use, so I understand that it's not ideal for me to write everything beforehand and then just talk through it. But since this is review material, I wanted to make sure it was neatly organized. So for this time only, I'm going to talk through everything that I've written previously. The first thing I'd like to discuss is how phase equilibria fits with the rest of the curriculum. I think this is a topic that sometimes gets lost in the introduction to many courses, and it's very important to me that you see how it fits into the broader picture. Because you all had me for material and energy balances, except for a couple of you, I know for a fact that you know how to solve for the unknowns if given a process flow diagram like this. So I took this exact process flow diagram from a homework statement that I've given in multiple semesters, so it may look pretty familiar to you. Remember how we solved the question, so there'd be a big paragraph up here that would describe the problem, and you would draw a box for each process unit. So we got a mix point in here, a reactor that is converting, it looks like methanol and chlorine, into a preferred product of methyl chloride with some dichloromethane and HCl as side products. That reactor has some specifications of a conversion of 90% and a selectivity of our desired to undesired product of 3. And then the problem statement specified that the separator would remove 80% of the unreacted reactants and recycle them to the fresh feed where it mixes before it goes into the reactor, such that we can improve our overall conversion from 90% to something greater. And then of course we have our outlet stream, which contains the unreacted reactant that did not get separated out, in addition to all of our products, desired and undesired, where it will presumably go for further processing to remove or purify our desired product. So remember, we can do a degree of freedom analysis. We can solve for each one of these unknown flow rates, these n dots. That's what we learned how to do in material and energy balances. And I've started teaching this in MEB, but just getting an appreciation for how grossly oversimplified this process is. Everything is represented by boxes and arrows. Flow rates are really the only thing that we have in addition to some other specifications here. But I want to call your attention to this separator. And it's really a magical kind of black box, and we don't really consider in MEB the logistics of how this happens. Think about how difficult this may be. You know, a chemical mixture is not very easily discernible as a mixture, and even harder to separate. So what is the mechanics behind how this separator just pulls out 80% of the unreacted reactants without pulling out any of the products? And as engineers, we should ask, can we do better than that? So what we just take for granted that 80% is what we've got, but can we get 90% or even 100%? Is it even possible to get 80%? What determines how much or how good this separator will act? And then there's the question of what process conditions should we use? So the separator's performance will be affected by certain process variables, namely the temperature and the pressure. And this class, Phase Equilibria, seeks to get at the fundamentals of how this stuff happens. So this whole idea of separation operations is the subject of a future class that you'll take, which I also teach, and I'm on the schedule to teach it in the fall when most of you will probably be taking it. So I'll see you there. And we'll discuss several separations methods. And by and large, distillation is the overall favorite of industry. And that operates under the assumption of vapor liquid. And those two things are phases of matter, which is where we get the name phase equilibrium, which is the title of this class. So again, this class is going to be the fundamental or theoretical basis that you need in separation processes. And then to a lesser extent, it also forms the basis of ECH 4504, which is chemical kinetics and reactor designs. There's also some phase equilibria stuff that you can look at with chemical reactions that we'll talk a little bit about at the end. So this whole idea of phase equilibrium shouldn't be a completely new concept. If you remember that weird interlude portion of MEB, so the first third of the class, we approximately did some material balances. The last third of the class, we did energy balances. There was that weird in-between part in there where we covered chapters 5 and 6 of the Felder-Rousseau and Bullard textbook, where we got into this phase equilibrium stuff. And in general, I want to call your attention to these TXY and PXY diagrams and remind you of how they work. So these are the plots where T or P is plotted on the y-axis versus X and Y are compositions in the liquid and vapor phase, respectively. There are two curves on a TXY or a PXY plot. For a TXY plot, the upper region of the plot is vapor. So again, don't memorize these things, just rationalize that mixture with a high temperature will tend to be a vapor and a low temperature will tend to be a liquid. And it's reversed for the PXY. So a high pressure will tend to be liquid, low pressure will tend to be vapor. The curve that is next to the vapor on both of those plots is the dew point curve, and the curve that is next to the liquid is the bubble point curve. Recall that the bubble point can be rationalized as the point in a liquid mixture at which the first bubble of vapor forms, and the dew point is the point in a vapor mixture where the first droplet of liquid forms. Recall how to read these diagrams. So in a TXY diagram, you are taking as an assumption that the pressure at which the TXY diagram was constructed is known and constant. So you have to know specifically what the pressure is for a TXY, and vice versa, you have to know what the temperature is for a PXY. Otherwise, if you don't have the PXY or TXY at your specified temperature or pressure, you need to obtain it. And if your coordinates of temperature and composition lie within this two-phase region, you will have phase equilibrium. So they have both vapor and liquid phases that are present. And in order to determine the composition of those two things, you can draw a horizontal tie line straight across. And where the tie line intersects your dew point curve will be your vapor compositions. Hopefully you can see my mouse pointer. I'll go back and look at this video later. And if that's not something you can see, I'll make sure to fix that in future videos. Where it intersects the dew point curve will be the vapor composition. Where the tie line intersects the bubble point curve is the liquid composition. And in this example, it should make sense that whatever component is plotted on the x-axis will be the more volatile component because the vapor composition is higher than the liquid composition. And everything that I just said holds true for the PXY diagram as well. The only difference is that pressure is your dependent variable, so you'd use that when determining what the coordinates are. So remember how you felt the first time that you saw a diagram like this? You may have been confused. I recall the first time I saw something like this and it didn't really make any sense to me. In other words, if I know that the pure component boiling point of a substance is 80 degrees and the pure component boiling point of another substance is 100 degrees, why should the fact that I mix them together change the temperature at which it boils? In other words, if I heat this mixture up to 82 degrees, regardless of what the composition is, shouldn't all of the more volatile component vaporize, leaving behind only the less volatile component? And it would be nice if life worked that way. Certainly separations would be a lot easier and cheaper to accomplish. But of course, life isn't so accommodating and it's a lot more complicated than that. So phase equilibria describes how these plots come to be. And the goal of this in the end is to predict this type of behavior such that we can design the separation processes that we use to purify the products. And then a little bit later on in the course, you'll learn that it's not even this simple. So those TXY, PXY plots that I just showed you were assuming Raoult's law with ideal behavior. And in Thermo 1, you learned about how ideal gases very rarely are the case. The ideal gas law is not the preferred equation of state. So real chemicals that are in a real mixture can behave non-ideally, or in certain extreme cases, they can form an azeotrope. And that's the word for the point at which the composition doesn't change upon boiling. For a TXY diagram with an azeotropic mixture, it can look very funky like this. So again, we'll talk about in phase equilibria how we model this type of thing and we predict this type of thing such that it can be used to design process equipment. That is going to be the end of my first video. I know that I went through that extremely fast. So if you have to rewatch this video, I highly recommend going through and writing this in your notebook. Again, this won't be the status quo for how I usually do videos. I just wanted to record these quickly since they're all review anyway. If you already know this stuff, just enjoy the feeling of being on top of the material for now. The sad truth of this subject matter is that it does get very complicated very quickly, and hopefully by slowing down and being able to rewatch the videos, it becomes more easily palatable. So I'll see you in the next video.